So this next part of the lecture deals with something that is called spontaneity. Now we have an idea of what spontaneity means, and we talked about it in an earlier lecture. Now we're going to explore it in a little bit more detail to see, can we determine if something is going to be spontaneous or not. So just as a reminder, this term spontaneity has a very different meaning in the language of chemistry. A spontaneous process is a process that can occur without the constant application of energy. It doesn't indicate that something is fast or slow. It just means that it can go from reactants to products in a forward direction without that constant application of energy. Spontaneous process always occurs in the direction required to reach equilibrium. Sometimes that's in the forward direction. That would mean if you have to go forward to reach equilibrium, that reaction would be spontaneous in the forward direction. If you need to go in the reverse direction to reach equilibrium, then that reaction will be spontaneous in the reverse direction and non-spontaneous in the forward direction. So let's look at spontaneous reactions. A lot of common spontaneous reactions are exothermic. Now, the problem with this is this leads to a lot of incorrect assumptions that spontaneous reactions are always exothermic and non-spontaneous reactions are always endothermic. And this just simply isn't true. There are spontaneous endothermic reactions. There are non-spontaneous endothermic reactions. There are spontaneous exothermic reactions. There are non-spontaneous exothermic reactions. And so whether or not something is spontaneous or not has nothing to do with whether it is exo or endothermic. A good example of a spontaneous endothermic reaction would be the dissolving of a very common chemical, ammonium nitrate. When ammonium nitrate is placed into water and you dissolve it, it gets cold. And it gets cold because the dissolving process is in fact endothermic. There are dissolving processes that are exothermic and dissolving processes endothermic, and they're both spontaneous. Other spontaneous endothermic reactions, the expansion of a gas. If you've ever had a container of compressed gas and opened it up and just let it go, you'll notice that that container gets very cold to the point of having ice build up on the outside, because as gas goes from something very close to something out, away from each other, it takes energy to expand that gas, and so it absorbs energy from the atmosphere, and so that is an endothermic reaction. If you are melting ice, if you're going from ice to water, if you are above 0 degrees Celsius, that is a spontaneous reaction, and it is endothermic. To go from ice to water, that ice has to absorb energy from the surroundings in order to turn to water, and that again is endothermic. So we have to get out of our mind that exothermic is always spontaneous and endothermic is not, because it can be either for either type of reaction. There are factors other than heat that influence spontaneity. So one of these main factors is something that is called entropy. Entropy is basically a measure of disorder. We give it the symbol S. Notice that it is a capital S, and because it's a capital S, this means that entropy is in fact a state function. Now you can get into the nitty-gritty of entropy. We're going to do that just a little bit, but not really into the math behind the entropy. If you go on to take a higher level physical chemistry course, you may explore it there. But this disorder within a chemical system is based on the number of occupied energy states versus the number of available energy states. So how many energy states do I have available versus how many have I occupied? For the most part, for a lot of chemical reactions, we don't need to get down to that energy state level. We can do visual inspections of a process to determine the entropy change of a system. Not always, but sometimes we can do that. A lot of times what we need to do, though, is to look at overall entropy changes to see what are the changes of the surroundings. So determining the entropy change of a system is fairly easy. However, determining the entropy change of the surroundings can be quite difficult if you're just trying to do that. Okay, so let's just focus on some systems here. When potassium chloride dissolves into water, so we have a crystal of potassium chloride, as we put that potassium chloride into water, it's like salt, like sodium chloride. Those ions are going to break apart from the crystal and now float around in solution surrounded by water. So those ions that were locked into the crystal are now separated around and floating. So you can see that the entropy of the potassium chloride is going to increase because they went from being highly ordered to very disordered. And in doing so, they increase their entropy. However, we think about the water molecules, and they're actually going to bind to those ions in there. So the entropy of the water has decreased. So we've had an increase in entropy in our system, but a decrease in entropy of our surroundings. So whether or not that process is overall a positive change in entropy or a negative change in entropy is very difficult to determine just based on this information. So for right now, the only thing we're going to focus on is the system. We'll get to the surroundings a little bit later. So we want to predict the sign of delta S system for these simple processes here. So we have H2O liquid going to H2O gas. You should predict that the sign here would be a positive change in entropy, which indicates an increase in disorder. We're going from a liquid kind of ordered state, the molecules are kind of attached to each other, into a gaseous phase where everything's moving around at a very rapid rate. So we have a high amount of disorder in a gas, a little bit of disorder in a liquid, and we have an increase in entropy. If we go from silver ions in solution plus chloride ions in solution to silver chloride in a solid, you should see that that is a negative change in entropy. And the reason why is because we have ions floating around in solution to being locked into place in a crystal, that crystalline solid AgCl. Just the opposite of what we saw for the potassium chloride in the previous slides. This one's a little more complex. We have 4 moles of iron solid plus 3 moles of oxygen gas going to 2 moles of rust, Fe2O3. Okay, we can look at some phases there. We see that we've got some solid and gas in the reactants and just solid in the product. To me, that would indicate that we are going to have a decrease in the entropy because the 3 moles of oxygen gas are going to have a fairly high degree of entropy, and all of that oxygen now is locked into a solid form. So that's probably going to decrease the entropy by quite a bit. Notice also that we're going from 7 moles of material down to 2 moles of material, and that indicates a loss of entropy as well. So if I had to guess at this, I would predict that this will have a negative entropy change, but in something like this, you really do have to do a calculation to verify that because there are some other things with entropy that we haven't really talked about yet. Well, that finishes out this portion of Lecture 5. A little bit of a short one there. We'll delve into more of the calculation of delta S for a reaction in the upcoming lecture part.